Infostralians.
In relation to the speed of light, makes the way just the way we've come to expect.
One of the beneficial effects of having the speed of light be as fast as it is that you see is what you get.
Light speed makes everyday experience virtually instantaneous. When the light bulb goes on, you see it right away. Everything that happens around you registers immediately. And certain experiences make it crystal clear that light travels faster than anything else, including sound.
One interesting consequence of the great speed with which light travels is that you see a flash of lightning essentially instantaneously, but you hear the thunder only later on.
But light speed has its limits when stacked up to a place as large as the universe.
We think that the speed of light is unimaginably fast on a human scale. However, in astronomical terms, it's actually kind of pokey.
And so it's ironic that when the Apollo spacecraft blasted into space, traveling at what seemed an amazing 25,000 miles per hour, the speed of light proved frustratingly slow when it came time to talk to astronauts 236,000 miles away on the lunar surface.
So when the astronauts were on the moon and people asked Neil Armstrong, "Hey Neil, what's it like up there?" Several seconds went by between the question and Neil Armstrong's answer.
Neil, with the Houston radio check over. Roger, Houston, line's clear. Roger, I'm clear, Houston. Roger, bud.
And those several seconds were not because he was thinking about the answer, but rather because it took 1.3 seconds for the signal traveling at the speed of light to reach Neil from mission control, and another 1.3 seconds for his reply using radio waves to come back. That's 2.6 seconds without even thinking.
Okay.
The 1.3 seconds it takes light to travel from the Earth to the Moon is pocket change compared to other celestial bodies. Light from the Sun, for instance, takes more than 8 minutes to get to the Earth.
If the sun were to disappear right now, if the sun were to suddenly vanish, it would take 8 minutes before we would even feel the shock wave and see the effects of a disappearing sun.
The limits of light speed also make communicating with Earth's far-flung spacecraft a special challenge. It takes up to 44 minutes for signals to travel back and forth to the probes exploring Mars. More than 3 hours to Cassini at Saturn. And over 29 hours to Voyager 1, the most distant of all, now heading out of the solar system. Still, these distances are trivial on a cosmic scale. We can almost understand the 10 billion miles separating Earth from Voyager. But what's next? The nearest star is a red dwarf named Proxima Centauri, nearly 25 trillion miles away. That's 25 followed by 12 zeros.
I am often asked the question, how can you as an astronomer really comprehend these vast distances, these huge numbers? And the answer is, I can't. The human brain really doesn't wrap itself around numbers that big. Occasionally, I actually write out how many zeros there are in kilometers and here the galaxy, just to see how huge that number is. But in reality, of course, as astronomers, we would be spending all day writing zeros unless we came up with a better unit to use. And that's what a light year is. A light year is approximately 6 trillion miles. It's the distance that light travels in 1 year.
Using light years to describe distances opens up another dimension